Wave-particle duality. What is that, you ask? It is quite simply the concept that light and matter can be described as both particles and waves. This depends wholly on the form of observation. At the beginning of the 19th century, Thomas Young devised the famous double-slit experiment, which is a way to test the wave properties of light. This was a great step in ending the centuries-old debate on whether light moved as a particle or a wave. This is a very simple experiment where monochromatic light is passed through a plate with two slits, which splits the light into two waves and then illuminates the screen behind it. As you can see, the wave nature of light causes the light waves to interfere, producing bright and dark bands on the screen, a result that would not be expected if light consisted of classical particles.
The reason this occurs is because the path length of both waves changes, resulting in a phase shift and creating an interference pattern. The video shows the experiment in action. You can clearly see the bright and dark bands produced as they change when the slit width increases and decreases.
For over 100 years, the consensus was that light passed as a wave. This all changed in 1905 when Albert Einstein published his Nobel-winning thesis. This explained the phenomenon known as the photoelectric effect, which is the production of electrons when light is shone onto a metallic surface. According to classical electromagnetic theory, energy is transferred from the light to an electron. This means that any change in the intensity of light would change the rate of electron emission. Also, a very dim light would be expected to show a time lag between the initial shining of the light and the emission of the electron. However, experimental results confirm neither of these predictions. Instead, electrons are emitted only when light reaches or exceeds a threshold frequency. Below this threshold, no electrons are emitted regardless of the light intensity or the length of time of exposure to the light. To make sense of this, Einstein proposed that light is not a wave, but a collection of discrete packets known as photons, each with an energy equal to Planck's constant multiplied by the frequency of light, E equals hf. This comes from Planck's quantization of energy, and Einstein showed that light can indeed travel as a particle.
The photoelectric effect was impossible to explain in terms of classical physics, and as a result helped propel the emerging concept of wave-particle duality in quantum mechanics.
Now we know that under different experimental conditions, we can experience light as both a wave and a particle. So what about matter? Louis de Broglie was the first to suggest the wave-particle nature of matter, and as a result won the 1929 Nobel Prize for Physics. For experimentally demonstrating the wave-like nature of matter, this formed a central part of the theory of quantum mechanics. Now it's time to get a little bit weird. In 1961, the double-slit experiment was performed using electrons for the first time. During his famous lectures, Richard Feynman spoke about the phenomena at length, stating that the only explanation for the interference pattern achieved is if electrons behave like waves. However, in 1971, the experiment was taken one step further when it was performed with a single electron being fired one by one at a detector. The interference pattern produced was identical to that of the original experiment, showing that each electron actually interfered with itself, as predicted by quantum mechanics. So after centuries of discussion in the physics community, the answer is actually that light and matter can both show wave and particle-like properties. The truth is, this is only the tip of the iceberg, as quantum mechanics gets a lot weirder, which you will soon find out as you continue to study physics. I hope this video has been helpful in understanding wave-particle duality, so please hit the subscribe button and check out our other videos.